Hello, everyone, and good morning to our session today. This weekend, we'll be talking about machine learning, and for that, we have an expert for you all, who's Snehanshu Saha. So Snehanshu did his master's degrees in mathematical and computational sciences at the Clemson University, USA, and his PhD from the Department of Applied Maths at University of Texas. After that, he joined PES University in Bangalore, where he worked from 2011. And recently, he's joined BITS Pilani, Goa. And we are very happy to have Snehanshu with us today because, we want to hear it from the expert. So over to you, Snehanshu, and welcome. Snehanshu, please unmute yourself. You are muted. Snehanshu? Hello.
Yeah. Sorry. Is it okay now?
Yeah.
So can you see my? Yeah. So can you see my screen?
No.
No. That is strange.
You have not shared it. You should reshare it probably. I don't know.
Okay. All right.
I think we can see the screen. I think we can see his screen. I was able to see the screen. Yeah, I can. I could.
Acha, then actually I'm using these double.
Screen was visible.
Yeah, it is. It's visible.
All right.
Okay. Then sorry. Then that's fine. So is PPT visible?
Yeah. So let's begin. So this session on machine learning / deep learning is will be split into two sessions. I mean, in the first session, that is today, I'll be talking on learning from data, the basic principles of machine learning. As I understand, the participants are, generally not exposed to the nuances of machine learning. And then I'll also focus on some of my work, which is developing new theory and methods in deep learning to classify astronomical data. So there are some problems that I work on, and I have been, asked by Priya to talk specifically about classification of extrasolar planets. I mean, in the context of whether we can, come up with some learning algorithm, some classification algorithm to figure out whether, based on what you learned in the past, based on some data that you have, if a new exoplanet is discovered, can you predict whether this new exoplanet is habitable or not, right? I mean, all of that is a bit tricky, but generally it follows the principle of classifying a new sample from existing data. Okay, so the first point is, you try to classify a new example, okay, from the previous one. So that means you should have a corpus of data available to you with class levels. Okay, so that means we have a corpus of data already available to us with class levels. I'm going to elaborate all of this one by one. So these type of learning, so this is sort of this we call as learning, right? And who learns? The machine learns. Okay, so the machine learns from the data, right? So the machine learns from data. Okay, and typically the kind of problems that we are going to talk about, the data is labeled. Okay, all right. And so this kind of machine learning is known as machine learning from the labeled data. Okay, or in other words, we can also call this as a supervised learning. The reason this is called supervised learning is because some kind of supervision is necessary, and that supervision comes from what sort of levels we already have on the data. Okay, if your data does not have levels, we cannot use this kind of supervised learning. Okay, now you have already seen that I talk about, I just mentioned class, right? So, just to give you an example, very simple example, let's say we are trying to detect cancer from some data that is given to us. Okay, all right. And so based on that, what we sort of do is that, so there has to be a representation of data, right? So there has to be a representation of data. Okay, and just so that machines understand, we need to have quantitative representation of data. We cannot really talk about data in the qualitative sense as we humans do, right? So when we talk about data, we typically refer to as a data matrix. Okay, which is nothing but a column vector. Okay, assuming that we have, and you have many such, data sets, and assuming that we have a number of data points, because depending on the number of sample, let's refer to the exoplanet catalog. Right now, we have about 4,300 discovered exoplanets, which is available in the Planetary Habitability Lab exoplanet catalog. And each of those planets can be considered as a data point, and each of those planets have some attributes. So from a physical sense, what you refer to as attributes, which could be like mass, radius, surface temperature, equilibrium temperature, eccentricity, luminosity, flux, etc., etc. All of these are physical attributes of a planet, right? So in the language of machine learning, these physical attributes are referred to as features. Okay, so data and features are combined together in a matrix, right? And that is known as a feature matrix. And going back to the exoplanet catalog, if you look at the exoplanet catalog at PHLEC, you will see that there are predominantly three classes that are mentioned. One is non-habitable, okay, which are actually the dominant class. Actually, about 90%, 92% of those discovered exoplanets are non-habitable, okay? And the remaining data points or exoplanets are labeled into two classes, cycloplanets and mesoplanets. And there are one or two samples of hypocycloplanets. We can ignore those for now, right? So at least as far as this particular data set is concerned, we have three classes, okay? All right. Now, what we want to know is that suppose we have these many samples, like 4,300 data points with three classes with a bunch of features. If new exoplanets are discovered, which is actually being discovered at a very speedy rate these days, right? Just to give you an example, in 2018, the PHLEC catalog had about 1,650 entries, and in 2 years, 2020, it's actually more than doubled, right? And the way NASA space missions and some of the Chinese space missions are going, I would expect these numbers to double up in the next year, right? Now, how many of these are potentially habitable is the question, okay? All right. So, the whole purpose of this classification task is to see if the machine could learn from the given data whether a new data point could be potentially habitable or not, right? Okay. So, also the cancer example, because when we talk about classification, as far as the exoplanet classification is considered, this is three classes, right? Non-habitable, exoplanet, and mesoplanet. Now, when we talk about the cancer detection, right, or the classification of patients of suffering from cancer and not suffering from cancer, this is just a two-class problem, right? So classification problems can be. So when we talk about classification problems, these are two-class or multi-class. Okay, and these two-class classification problems are also referred to as binary classification problems. Okay, all right. If you have any questions, please keep typing in the chat box, because right now it will be difficult for me to migrate between the whiteboard and the Zoom interface, right? And I'll take your questions. I mean, I'll probably talk about about 20 more minutes and take your questions and come back to my lecture, right? Okay. So the two-class problems are easier to solve compared to the multi-class problems. So to give you an example, it's like if a patient has cancer or doesn't have cancer, right? Okay. So, I mean, how are you going to, I mean, if you think about this problem in a low dimensional feature space, right, where assuming you have just, one feature or two features, I mean, how do you visualize this problem? Because the moment typically what happens is when you look at a feature matrix, I mean, I gave you the example of the exoplanet catalog, right? When you look at an example of a feature matrix, it has many, many features, and each feature corresponds to a dimension. So when you have a many feature problem, you are no longer in a position to actually visualize that data in the features, right? But if you have a low dimensional machine classification problem, you have the luxury of at least be able to draw a picture and try to figure out what is going on, right? So there are several machine classification problems. One is a classification problem and the other one is a regression problem. And then there are unsupervised problems as well, okay? So classification is not the only machine learning problem that people work on or talk about, right? So these classification problems are very closely tied to a regression problem. Okay, in fact, most of the early advances in machine learning owe a great deal to the theory of regression. Okay, now, so just to imagine this, let's see if we can sort of picture this out in the following sense, that I have this mapping, right? And what X is that there is a set of data points. So I can just, represent this as X to the power I, and I can actually correspondingly represent the values of Y as Y to the power I. So in the sense that any data point that I have in the two-dimensional feature space, I am able to represent this as xi, yi, which is an ordered pair of data points. And where your xi is typically the input, okay, and yi is the output. Now, I think you know a little bit about regression, right? I mean, some of you may be very, very familiar with how regression models work. I mean, which is this following manner, is that I do have a hypothesis. So let's say I have some data, okay? I have some data which is scattered in the feature space, okay? All right, and these are all my training data. These are the data points for which I have the values of both X and Y available to me, which is why regression is actually a supervised learning problem, right? And I have a hypothesis, which is the following. The hypothesis is that I think, and the moment someone says, I think, you know that there is some bias associated with that person's thinking, right? So there has to be a bias. So if a human has bias, that bias will also transport to a bias term in the machine learning context, right? So if you think that there is some model, in this case, a straight line, that will fit these data points quite well, okay? You will just think of this as a particular regression line, which will fit this data point quite well. However, another person, okay, can think, well, I could probably, I could probably, tilt this line slightly to the left or slightly to the right, so that I might have a better fit. Unless you quantify the error of your prediction, you really do not know, visually speaking, that whether this is a better fit compared to another model that somebody else has proposed. So we have a bunch of hypotheses, right? Okay. So you have a hypothesis, right? Okay, all right. And let's say your hypothesis is something like this. Your hypothesis is you think that your regression model is something like this. Okay, now if you really want to write it in a more compact notation, I mean, you could think of this as theta transpose x. I hope you are exposed to the basic concepts of linear algebra, right? I mean, which means there is a theta vector which is from theta naught to theta n, and then there is an x vector which is the data vector which is from 1 to xn. Now, how do you know how good your hypothesis or model is? It actually depends explicitly on how well you can measure these guys, right? Which are the coefficients of your regression model. And you can see there is this term theta naught, which is nothing but the intercept. If you think of in terms of a straight line, and this is your bias term, because the moment you start tilting your model so that you think it's a better fit compared to the another model, you have to change this value of theta naught, right? So you are changing the bias term, correct? Okay. And if you change the bias term, you can get another model. And you change the bias term again, you get another model, right? So therefore, you actually have a bunch of hypotheses in your hypothesis space. Okay, all right. And each one of those hypotheses is actually associated with a different bias term. So in your machine learning model, there is bias, okay? And then also there is this thing known as the variance, right? So let me just say this at this point of time, just to introduce the keywords. So there is this bias, okay? And look, if you change the model, which is you are tilting it right now, as simple as that, your model may be a good fit or maybe a worse fit. How do you know your model is a good or a worse fit? Is that what you try to do is that you have all of these points, right? So what you try to do, you actually start dropping perpendiculars, okay, from each one of those data points on the line, okay? And what are these perpendiculars going to do for you? They're actually going to measure the deviation of each of the data points in your training set from your fitted model, right? Okay. Now, some of the, as you can see, some of these data points are above the line, some of these data points are below the line, and based on the signs associated with this, there could be positive distances as well as negative distances because of the orientation. And this is the reason people consider not only the difference between those, that they actually square the distances, each one of those distances, and take the sum of all the distances, right? And what they argue with a solid mathematical argument is that if the sum of the square of the distances is a minimum, then my model is a very good fit, and I have been able to estimate or measure the coefficients, pretty well. Okay, all right. So therefore, this is known as the variance, or we actually measure this in terms of a least squared function. Okay, all right, which is nothing but, I mean, this least square function is nothing but, you have to be able to define something like a cost function, because there has to be a cost of misclassification. There has to be a cost of back prediction, right? And you would want this cost to be minimized. So this cost is actually a function of your parameters theta. This theta implies across, like theta naught, theta 1, theta 2, all the way, right? And what you do is that if you have a number of training examples, which is m, depending on the number of training examples that you have, which is nothing but the total number of data points that you have is this. Okay. So the idea is simple, is that you have this guy, which is nothing but your actual values, right? And you have this guy, these are your model values. So these are your predicted values and these are your actual values. Or you can say that this is your target value and this is your actual value. What you want to do is to minimize the distance between your predicted values and the actual values. Ideally, what you want is this guy to become 0, because if this guy becomes 0, then you have fitted the model quite well. Okay, all right. And since all of these data points are given to you a priori, this is also known as a supervised learning problem. In other words, regression problem, and it is strongly related to any classification problem that we wish to solve. Okay, so this thing is known as a cost function, because these are important terms if you want to understand and apply machine learning to do projects in astronomy or any other branch of science and engineering. So this is a cost function. Okay, so the job of a good learning algorithm is to be able to minimize the cost function. Okay, all right. So people also call this an error function because this comes from a least square error, right? Okay, all right. So one of the things of being able to use a least square error is that you implicitly assume that your errors are normally distributed. Okay, so if your errors are normally distributed, which is an assumption in regression problem, then you actually should be in a position to use the least square cost function. Okay, I mean, I actually know many people who by default assume that the errors are normally distributed, but I don't think that's the right approach, because there are other loss functions based on how your input data is distributed as well as how your errors are distributed. So it is always a good thing to check beforehand, before you decide what kind of loss function you are going to use, is to look at the error distribution, okay, whether it is normal or not. Okay, I'll give you an example from astronomy. In fact, this is an example from redshift estimation of galaxies, okay, and based on a number of features. And this is a regression problem. And I have looked at some of these papers published before, right, in the last 2-3 years using machine learning and regression, and they have assumed the errors to be normally distributed, okay. And now this particular galaxy data keeps on updating, and now we have a whole lot of galaxies whose redshift can be estimated. When we plotted the error, we did not find the error to be normally distributed. And since the errors are not normally distributed, it would have been a cardinal mistake to assume that your cost function is a squared loss. Okay, so there has to be something else as a cost function. Okay, however, there is another nice incentive of using a cost function like this. If you look at this cost function, it's a squared function, right? So it's a quadratic expression. Now, the nice thing about a quadratic expression is the following. A nice thing about the quadratic expression is the following. So let's say I have this cost, loss function, right? Okay. So a nice thing about this quadratic expression is that you have your loss is actually smooth, right? This is smooth. Also convex. Okay, all right. And I mean, if you look at it visually, inspect this visually, you will see there is a minima that you can see, right? Now, typically this cost function, as you can see here, your cost function is a function of theta. Okay, these thetas are also known as the weights in a machine learning problem or a regression problem. So in general, this j theta can also be written in the following manner, which is more of a standard convention these days, that people call this a cost function, which is a function of the weights in your model. Okay, weights and biases, right? So when you plot this is because the idea is this, that if you have chosen wrong weights, you have a bad model. If you have chosen good weights, you have a good model. So whatever error you are incurring in your prediction or classification is primarily because of the choice of wrong weights in your model. So what you do when you minimize the cost function, you write the cost function as a function of the weight, and then you use some Lagrangian or a partial derivative, compute the gradient, and see where the minima exists. Now, typically when you have a convex smooth loss function like this, which is nothing but a soup bowl, right? It's basically like this. You traverse from any point in that soup bowl, and you are sort of guaranteed after a certain number of iterations to come down to the minimum point. Okay, this is why people like this particular kind of a loss function, even though sometimes it is not statistically correct to assume so. Okay, all right. So now, having said that, so if now let me first present the connection between the regression problem and the classification problem, and then I'll come back to this cost function again. Okay, all right. So let me save this first. And I'm going to share these whiteboards with you as well after the end of my talk. Okay. All right. So now, so what have we learned so far? We learned that there is a regression model, right? There is a regression model, okay, which is primarily a prediction model or a forecasting model, okay? And it's sort of, by the nature of it, it is continuous, okay? And then there is a cost associated with your learning model. And this is typically represented as a function of the weights, okay? All right. So in order to learn things well, what we need to do, we need to minimize the cost function. Okay. All right. So, I mean, if you really think about it, your classification problem or regression problem is actually most of the times an optimization problem. Okay. So this implies your classification problem is actually an optimization problem. Okay, which is why people actually love these squared loss functions or the mean square cost function, because since mean square cost function is a convex function, this kind of optimization problems become a convex optimization problem, and these are easy to solve. Moreover, every convex optimization problem guarantees a theoretical global minimum. Okay, so every convex optimization problem, every convex optimization problem guarantees a global optima. Okay, and since there is an optima always corresponds to pretty good measures of pretty good classification accuracy. Okay, so these are some of the fundamentals of. Okay, I'll just look to the chat. Okay, no, a problem which is a convex optimization problem is that first of all, the trajectory, the loss surface has to be smooth. It cannot be bumpy, right? And there are ways to check if a function is convex or not. There's a standard property that the loss function that you are trying to optimize, whether this is a convex or not, because if you draw a tangent line, right? And this, if it's a concave problem, the tangent is always lies above every data point in the curve. If it's a convex problem, the tangent line always lies between every data point in the curve. In other words, I mean, I'll tell you, it's a good question, right? I mean, I'll just give you an example. Is that something like this? Let's say I have a surface like this, and you are trying to optimize on this surface. So you pick any 2 points, right? Okay, and you draw a line segment joining these 2 points. Okay, and I'm assuming that this is a solid surface. This is a solid surface, not a hollow surface. which means I have connectivities defined and it's dense in the sense that there are a lot of data points inside this solid surface. Professor Hassan here, Nazam Saab is an accomplished mathematician, so he knows, I mean, he can tell you more about, dense objects mathematically, what it means, right? But for now, you just think about this as there are densely connected data points inside the surface, right? If you do not have densely connected data points inside the surface, you can call it a hollow surface. Anyway, so the point being, if you pick any 2 points on the surface, right, and draw a line segment connecting the two, the line segment will in its entirety belong to this surface itself. So if you have such properties, right, I mean, there is an analytical way to represent this. If you have such a property, you call such functions as convex function. Okay, like for example, if I take something like this, some surface like this, I take a data point here, I take another data point here. Okay, all right, and I draw a line segment. What do you see? You see that the line segment, not in its entirety, belongs to that surface itself. So there is a closure property problem. Okay, so this is a convex set, right? So this is a convex set, and this is a non-convex set. Okay, so convex functions define non-convex set is a convex optimization problem. There are convex problems and there are concave problems like convex functions, concave function, and there are plenty of functions in the world, in real world optimization, which are non-concave and non-concave. In such cases, the optimization approach is completely different. We actually cannot take a calculus-based approach. So far, what I have been talking about is a calculus-based approach. Okay, all right. So now, I mean, having said that, I should now come back to this particular stuff, which I promised I would talk about, which is the relation between the regression problem and a classification problem. And please recall the binary classification, cancer classification problem, which has 2 classes, class 1 and class 2. Okay, now I will go back to the same hypothesis model that I proposed before, right? And which is your hypothesis H on the data is represented in the following fashion: theta naught plus theta transpose x. Okay, all right. And if you want to squeeze this into this term, you can also do that. In that case, your data matrix will be 1, x1, x2, x3, all the way up to xn. Okay, so let's do that. So let's just squeeze everything here so that your, theta is nothing but theta naught to theta n transpose, right? And your x is, 1, x1, x2, all the way up to xn. Okay, all right. Okay, so it has to be, actually, this is not a transpose. Here you could have this as a transpose, so that you are multiplying an n by 1 with a 1 by n, and you get a n by n feature matrix. Okay, now the thing is that assume that there is some threshold. Now we are back to binary classification problem. Okay, but we are using the model that we used in regression. Now, what will a regression model do? For each one of these input values, a regression model will throw you a number, isn't it? Right? I mean, at the end of the day, because the theta transpose x, also if you know a little bit of linear algebra, a theta transpose x is nothing but an inner product or dot product of x and theta, right? So, inner products defined on real vector spaces or complex vector spaces throws a number back at you, which is a scalar, right? So each and every time you do this, this hypothesis or your model will give you a number. And this is the number that you are pitching as your target. Predicted value, right? So this is a number that you are actually pitching as a predicted value, right? And then you have an H target, which is the actual value. And what you want to know is how close this H predict is to the H target, right? But this is like a continuous way of thinking about it. If you do not want to, just look at continuous numbers for each and every data point, but rather you would like to define a threshold in the following sense, that you have some graph here, and you define a threshold, let's say h of x equal to 0.5, and this is sort of arbitrary, okay, and this could change, right? And you say that whatever values of h of x are above 0.5, I will term it as data points belonging to class 1. This is what I'm going to predict. And whatever values are below h of x is equal to 0.5, I will term those as class 2. Okay, all right. So if you are doing that, so this is class 1. So what is class 1? Class 1 is, what you are saying is that my theta transpose x greater than 0.5. And this is class 2. And what are you saying? You are saying a data point or a new data point will be labeled as class 2 if theta transpose x is less than 0.5. Now, this choice of 0.5 is purely empirical, right? I mean, this could be right, this could be wrong. And standard question would be, how do I know this is right or wrong? This has to be done experimentally. If you do it this way and you see that your accuracy is really bad, I mean, you are actually flagging a lot of false positives or a lot of false negatives, right? Then you can actually modify the value of this h of x. You can slightly turn it up, you can slightly turn it down, in the sense that you can push this line slightly up, right? And you can form a new line, and then your threshold will become, let's say, h of x equal to 0.65. Then you will have a new decision logic. Theta transpose x greater than 0.65 belongs to class 1, else belongs to class 2, right? What happens if h of x value is exactly on the line? We do not know. We do not know whether it belongs to class 1 or class 2. And these are called regions of confusion or points of confusion. Okay, all right. Okay, so this is the relation between, so you are pretty much using a regression model, but you are not returning, instead of returning the output variable or the target variable vector as a continuous number or a real number, you are assigning a class to both of them based on some training data which you have already known. Okay, all right. So this is the relation between a regression problem and a classification problem. And so therefore, you imagine this, right? You know this, right? That whatever other principles in the sense of your loss function, convexity, smoothness of the problem, those paradigms do not change. So the principle of working out a good regression model based on a minimum cost function stays consistent when you convert the regression problem to a classification problem. I'll give you one more example of converting a regression problem to a classification problem. Let's say we have some stock data, stock market data. Okay, what you are trying to figure out is your output variable, which is the stock value. Now, stock values depend on a lot of factors. There are some technical indicators. There is a volatility term. There are also other things such as which particular sector this particular stock belongs to. Does it belong to a consumer sector like an FMCG? Does it belong to a healthcare stock? Is it something like an oil and energy stock? So depending on that, and some sectors have more volatility compared to some other sectors. Like the products which are typically in the health sector have less volatility, and those, it's easier to predict those stock values. Now imagine this. Typically what people do is that they employ a regression model, whether it's a linear regression or a logistic regression or so on and so forth, right? They employ a regression model and they try to predict the exact value of the stock. Now, instead of doing that, if you simply want to translate this problem to a classification problem, how are you going to think about it? The way you are going to think about it is that if I just want to see if the price of a particular stock is going up or coming down. So if it is going up, that belongs to class 1 category. If it's coming down, that belongs to class 2 category. And that's all I want to figure out. Okay. One reason why this is fascinating to most of the people in machine learning, or those who want to do work in this particular area or are already established experts, is that it reduces your risk of prediction to a great extent. Okay, because of the volatility of the nature of stock. So what you are doing, instead of trying to predict every single value to an very good precision, you're actually trying to club values to a range of values, and you are actually classifying those range of values as class 1 and range of values as other range of values as class 2. So this is a more safer and more robust approach, right? Where you do not run the risk of doing a very bad prediction in the sense that your predicted value is far, far away from the target. Okay. All right. So this is the connection between the regression problem and the classification problem. Okay. Now, what I want to also say is, at the end of the day, the bottom line is always this, that how do you make changes in your input matrix, since a huge difference between input and output matrix will make the cost function look really, really bad, and the task of classification also becomes very complex, almost untenable, right? However, if the input matrix is changed slightly, and you look at the overall change in the output, right, as compared to the change in Y, that is particularly helpful. What I'm trying to tell is that the gradient of the cost function tells us how we decide which components in input should be changed and by how much. And this is primarily determined by these guys. This theta guys, or the weight guys. You can think of this as the weight. Okay. So whether you are doing a classical machine learning or you're using neural networks, okay, these change in weights and updating the weights is a key factor in your eventual objective of converging to a minimum cost and therefore very good classification. So the bottom line is this: change, update weights, change, update weights. Okay. Minimum cost, good classification. Okay. Irrespective of the kind of data that you are working on, whether it is an astronomy data or data from some cyber physical systems and all, this principle doesn't change. So that's the reason we always try to look for a loss function which is differentiable, because how are you going to change and update the weights? How are you going to measure whether your loss function is, coming down or not, right? You have to do this, correct? You have to do the following. So this particular, since you are talking about changing the gradient, right? And recall our image, right? That your cost is something like this, and you are trying to come down, right? So there is a change in gradient, right? So therefore, there has to be a way to quantify this particular gradient. And we call this the error gradient, right? Error gradient or the cost gradient. And what is this? We define this, or we represent this mathematically in the following manner. This is a vector, but I'm just going to skip the vector notation. Okay, so just assume that this is a vector. And this is, what is this? This is nothing but, right, all of the weight vectors that you have in your classification problem. Sorry. Okay, all right. And then you have a training rule or an update rule that you employ. So suppose you have chosen a wrong value of the weights. You need to update the weights, right? And the updates are a small increment from the previous weight. And this is done by, since what you really want to do when you are solving a minimization problem or minimization error, right? You have to have a negative sign. And then there is a tuning parameter which controls the rate of change of your weight, okay, multiplied by these partial derivatives for all values of I from 0 to n. So you have to do it for each weight component. So if you have seen so many partial derivatives here, you must know each one of these partial derivatives is associated with the corresponding weight vectors, right? Okay, all right. And so therefore, you have to be able to update this. How are you going to update this? Is in the next slide. Okay, and then I'm going to come back to my talk. I mean, to come back to the slides, right? Or maybe I can do that tomorrow also. We'll see how it goes. Okay. Okay. So I hope my handwriting is fine, because the other day, Priya, I uploaded a sample of my whiteboard. When I first tried using my whiteboard, I uploaded a sample to Facebook, and then Priya commented, "Oh, it looks so bad." I guess, you know, it's looking at least, you know, legible now, right? Okay. So you know, we are talking about the cost function, right? We were talking about the cost or the error gradient. Okay, so what is this? This is your general representation, or your cost of error gradient is this. Okay, it is what you do is you have to define an error function, and as you have seen from the earlier slide, this error function for all practical reasons is chosen to be a quadratic convex function, which is nothing but a least square error. And there is this just regularization term that we add, and this should be simple enough. Is a squared loss. Okay, now what is TD? This is D stands for data, and this is the target, and this is what you have, your model has outputted, right? So this is nothing but your model output, whatever model you have chosen, model output, right? And this is your target. Okay, which means actual. Okay, now I think it should make sense of why this is actually a error function. Now, you are all, I mean, smart students, I hear, right? So you would know, I mean, we have to employ a sort of a chain rule. You're familiar with chain rule, I guess. So this 1/2 is a constant. I pull this out, right? And what I do is that I have to employ this chain rule, which is first you do the outside, which is 2 times TD minus OD, right? And then you have to bring this partial derivative inside, right? Like this. Okay. Now, this will mean this 1/2 and 2 will cancel out, right? You have TD minus OD, right? Which is the difference between the target and the output. And what is this going to be? What is this output? This output, I mean, is actually your model output, right? And we know, we have already seen, your model output is nothing but a weighted combination of your data. So this is just a dot product of your data matrix with the weights. Please mind that all of these guys are vectors. I'm intentionally not using the vector notation, right? Because it's too much. Now, when you do this partial derivative, what you have is nothing but minus x. Okay, all right. And then for every weight vector, for every weight, you update the weight in the following manner: yi minus 1. Okay, or rather, I mean, okay, that's fine. I'll just explain what I mean. Minus mu delta E delta. Okay, so previously you probably have chosen wrong weights. Now you know this partial derivative, and this is a hyperparameter that we have to choose conveniently. This is a hyperparameter, right? That we have to choose conveniently. This is known as a learning rate. Okay, in the language of machine learning, this is called as the learning rate. Okay, and this is known as the gradient descent update rule. Okay, all right. Okay, now we will use this gradient descent update rule on the training examples. But before I move on further, okay, I would like to go back, because I mean, Priya wanted me to talk about astronomy data. and how we have applied this on the astronomy data. I mean, a major part of that data exploration is actually reserved for tomorrow, where Dr. Mathur will show you from the Python notebook how certain methods written by us can be implemented. Okay, but at least today I'm going to give you some overview, right? So the next thing that I want to talk about is how we used neural networks, artificial neural networks, and deep learning to handle astronomical classification problems, right? But before that, I need to tell you what a neural network is, right? But even before that, what I actually want to tell you is that what is the connection between all of this, okay? So we started, if you recall, we started from a regression problem, right? We started from a regression problem, and then we gradually moved to classification, right? Now, in this particular context, I would like to introduce a very useful tool, which is known as a logistic function, because this is the same logistic function that is used predominantly in neural networks. Okay, so you know what a logistic function is. A logistic function is y equal to 1 over e to the power minus 6. Okay, it has some nice properties in the sense that for certain range of values of x, the function is monotonically increasing and it tapers off at the end, right? Okay, so but in the context of the data, when you are talking about the model, we'll just modify this in the following manner. Okay, where I will replace the x with a w transpose x, which is a weighted combination of my data and my weight vectors. Okay, and then I will measure what the value of this y is. Okay, all right, because logistic function sort of gives you a very nice, I mean, it sort of looks like this, right? I mean, sort of looks like this, right? Okay, all right, and you can sort of set a threshold somewhere over here, right? And you can say whatever if the y value is greater than this, let's say this threshold is 0.5, this is 0.5, then I have class 1, and if it is y is less than 0.5, the data points will belong to class 2. So instead of using a linear model, I'm now using a non-linear model, because non-linear models actually approximate data in a much better fashion than linear models. Please understand that machine learning, deep learning, neural networks are actually function approximators. So you learn your function, a non-linear function, from data. And it is clearly evident from a rich theory of calculus is that non-linear functions learn data, complex data much better than the linear function, which is why I'm now changing my model. Okay, that's one reason. And the other reason is this is also, in the language of neural networks, is known as a sigmoid function. Okay, or also known as sigmoid activation. Now, what does it activate? If you go to the neural network route, which is a pretty superficial mimicry of how the human brains work, inside our human brain there are a number of neurons, right? And some of these neurons are connected to some other neurons, some of the neurons are not connected, right? But what we do is, when we design a learning model based on the neuronal behavior inside the human brain, what we assume by default is that all the neurons are connected to all other neurons. So it's a fully connected artificial neural network where your input data is considered as a bunch of neurons, and you connect those input data to some other neurons through a combination of weights, right? And then how are you going to connect this? So in other words, you also know that neurons do not remain active all the time. So you have to activate the neuron. So you have to push a trigger, right? So this trigger is done by an activation function. So what you think of it in terms of as a classification logic can also be thought of as an activation logic, which means if the activation value, if I want to trigger a neuron, I need to, provide an activation. If the value of that activation unit is greater than some threshold, right, then the neuron will fire, and then I'll have some connection between my input data and some other neurons, and so on and so forth. Okay. So at this point of time, I think it's a good thing to just mention here what an artificial neural network is. An artificial neural network. So hopefully you see the connection between classical machine learning thinking and artificial neural network thinking, right? We are using some of the same tools in classical machine learning, which is what is known as a regression problem is now being converted to a classification problem via artificial neural network. What is known as a logistic regression problem or a logistic loss function, a logistic function is now being termed as sigmoid function, and it's being used to activate neurons, okay, to fire them. All right. However, the idea of this whole thing, because I mean, I have been doing this kind of work in astronomy for a very, very long time, at least for the last 4 or 5 years. And so there has been a lot that we have done in the last 4 or 5 years, and it's very difficult to present everything in 1.5 hours. So I'm going to say this, but before that, I'll just, just save this first. Okay. So why am I talking about all of that? What is the context? Okay, so the context is the following. In fact, if I have to present a full spectrum of my work, there is a significant modeling that we have done as well. Now, habitability scores, I mean, this is one particular area of research which is by, driven by Schultz-Marcuse, Abel Mendez, and a lot of other guys, right? And they think that exoplanets could be quantified by, giving every exoplanet a habitability score. And typically, a habitability score is given in the range of 0 and 1. And they say that Earth is the only habitable planet, right? And in that sense, Earth is an anomaly, that Earth's habitability score is 1, right? And you assign some habitability score to every other exoplanet, okay, between 0 and 1. So the planets whose scores are sort of closer to 0 are naturally planets which are potentially less likely to be habitable. Planets whose scores are closer to 1 are potentially more likely to be habitable, right? I mean, this is not a foolproof logic, but this is one approach, right? This is a modeling approach. Okay, so in that context, right? So assume that we have some model, right? Okay. All right, and there are different models like planetary habitability. There are different indices like planetary habitability index, and the most popular is that the ESI, which is you give a score to an exoplanet in the context of how similar that exoplanet is to the Earth, right? And so this is known as an ESI, right? So there is this PHI, right, planetary habitability index, and then there is Earth similarity index, right? And then a few years back, we proposed a CDHS, which is Cobb-Douglas habitability score, which is inspired from an econometric model. Okay, I don't have the time to talk about this, but the point being, I have some value for every planet. Okay, I have some value for every planet. Okay, however, unlike PHI and ESI, our CDH values, unless you normalize this, are not between 0 and 1. It could be way over. But then our logic was that it has to be in the range of Earth's CDHs, which is once again 1. Now, when you compute these habitability scores, there are some physical attributes that you consider. So in ESI, the physical attributes that were considered are mass, radius, surface temperature, and escape velocity. Okay, we added one more term, which is the orbital eccentricity to the model. Okay, all right. So there is this modeling approach. So here is this modeling approach where you compute explicit habitability scores for every planet. And then there is this classification approach where you do not compute any habitability scores, but rather you try to classify, new planets based on training data. The reason I even care to invoke this modeling approach is because we believe that there is some sort of, meeting ground for this. So what we had done, okay, was that we sort of listed out a set of candidates, a set of candidate exoplanets, which are favorably placed from both of these approaches, in the sense that those exoplanets are pretty good habitability scores, in the sense that they are close to Earth in terms of the habitability scores. And mind it, when you are computing these habitability scores, you are only using 5 physical attributes. Okay, mass, radius, surface temperature, escape velocity, and orbital eccentricity. And we have done this only for rocky exoplanets, because rocky exoplanets have a solid surface. Okay, we haven't done this for gaseous ones, because for most of those gaseous ones, you really do not know the surface temperature. You estimate the surface temperature from an equilibrium temperature, which is itself problematic one. So we have just taken the set of rocky exoplanets, which are about 1700 at this point of time as we speak, right? And then we have done the classification of those rocky exoplanets, and we wanted to see this, okay, that say, let me use a different color. So say there is a planet 1, P1, okay, whose CDHS is 0.95. You know that Earth CDHS is 1, right? So from this particular approach 1, this planet is favorably placed to be a potentially habitable exoplanet. Now, what we also do is that we do this classification approach, which means based on the training data, we try to predict the level of this planet, right? When we do this, we are not computing the habitability score. Also, there is another difference. When we are doing this classification, we have about 53 physical attributes that we are using. When we are doing this modeling, we are actually using only 4 or 5. However, if you want, you can extend the model, because we have also shown theoretically that our model is scalable under the assumptions of convexity. And that is something different that I don't want to talk about. But however, as of now, this modeling approach is based on 5 physical attributes. This classification approach is based on 53 physical attributes. And let's say the same planet P1 also turns out to be a psychro or meso planet. Then we have an enhanced confidence, and these are all statistical confidence. Okay, don't put me by the sword saying that, oh, why are you saying this? We physicists don't agree. I know you don't agree, right? But this is a statistical approach. So when I say confidence, I mean there is some statistical confidence based on which I can say that this is a favorable candidate. This planet P1 is a favorable candidate because its habitability score value is close to Earth, and also from a machine learning approach, it has been labeled as a psychro or a mesoplanet. Okay, all right. So we have done a fusion of these 2 approaches, okay, and that paper was published in Astronomy and Computing in 2018, and an enhanced version where we actually included the eccentricity as an additional physical parameter in the modeling approach was published in the same journal this year in January, right? Anyway, but in both of those papers, we have shown this fusion approach, saying that we really don't want to say that a particular planet is a candidate for being potentially habitable merely by computing its core or merely by classifying the planet by using machine learning. We will do both, right? And then we will see if there is a reduced set of such planets which satisfy both of these favorable criteria. Okay. Turns out, I mean, if you really adopt this one approach, you have a more optimistic set of potentially habitable exoplanets. If you go to Abel Mendez's website, he actually lists 43 planets as an optimistic set of habitable exoplanets. So ours, I would not say pessimistic, but ours is a more graduated list, and our set contains only 11. Okay, because it has to satisfy both of these criteria. So this is the context of doing all of this. Okay, all right. Okay, so now, I mean, remember, and when we are doing this classification, we took a deep learning approach. Which is artificial neural network based. Okay. When do I call an artificial neural network a deep learning network? When you have many layers. Okay. All right. Now, artificial neural networks could be shallow or deep. A shallow artificial neural network is one where you have one input layer where your data sits, and then you have a hidden layer, and then they have an output layer. A deep artificial neural network has an input data and an output data, and between the input layer and the output layer, there is more than one hidden layer. Okay. The reason why deep networks are preferred is because it is believed, and there is no theoretical evidence yet, okay, and some of us are working towards it, that if you have many layers, then you actually learn your features very well from the data, which features to use, which features to drop. Okay, all right. Okay, now I really don't have the time to talk about the dimensionality problem or the feature problem. I mean, if your classification problem has many features, it will actually impede the classification process. It may slow down, or it may actually affect adversely towards the efficiency of your classification problem. So which is why there are a lot of dimensionality reduction or feature reduction techniques that are being employed. Okay, but I mean machine learning is a very dense and a large subject, and that is the reason I shared my book with Professor Hassan, and I gathered that she has in turn shared that book, and that book is written to make you understand lot of the basic tools in machine learning that you need to study before you embark on any one of these projects. Okay, all right. So having said that, let me now talk a little about neural networks. Okay, please understand, a neural network works pretty much the same way, which is that I would want to predict the level of a new data correctly, and if I have not done it correctly in the first iteration of the first pass, I need to go back, do it again, come back, go back, come back, go back. So these forward and backward passes go on for a certain number of epochs, right? Until I reach what? Until the error becomes really minimum, and I cannot tangibly or practically improve upon the error. Okay, so let me present the schematics of an artificial neural network here. The schematics of an ANN. Okay. Now, what it means is that, as I said, there are some, each data point, okay, you think of it as a neuron or a cell. Okay. Now, if you are solving a regression problem, what is your output? Your output is just one value, right? So if you're solving a regression problem, you will have just one neuron at your output layer. Okay. But if you are solving a classification problem, let's say the cancer detection problem, where there are two classes, you will have two neurons in the output layer. Okay. This neuron will consist of all points which belong to class 1, and this neuron will hold all data points which belong to class 2. Okay, and then in between the input layer, so this is your input layer and this is your output layer. In between the input and the output layer, there is a hidden layer. So let me just, consider some number of neurons in the hidden layer. Okay, and as I said before, we are considering a fully connected neural network, which means that we have all of these guys have to be connected to all of this. Okay. So that is why it's called a neural network, right? Okay. Now, as you can see, when I start, right, these are my data points X. Okay. Now, these in the notation that I have been using just to be consistent, these are just Xi's, right? And this is a column vector. Now, we have a bunch of weights here, like this is W1, whatever, right? We have a bunch of weights. Okay. Now, so therefore, you are looking at a inner product of W and X. Okay. So this is a combination. How are you going to pass this from the input layer to the hidden layer? You need some function, right? You need some mapping between the input layer and the output hidden layer. And that mapping is achieved by the activation function. You remember I spoke about an activation before, the logistic activation or the logistic function, right? And then again, so you have, when you do that, you have some values over here, and then you apply the same activation function again, so that these values are then carried forward to these output layers. Okay. Now what you do is that you already have some training data here, so you already have some values that you have stored, which you can compare, right? So you got to compare these output values that your model has produced and the actual values. You see that whether the difference between these is small or large. Okay, assuming that the difference is small, meaning your cost is less, then you stop. Okay, you have learned perfectly in one shot, right? However, most of the time that does not happen. So this is your forward pass. When you are doing this, this is your forward pass, right? This is your forward pass. Okay. Now, if there is a bad cost, really bad, then I have told you this cost function. This cost function is nothing but a function of the weight. The reason why you have a bad cost is probably because you have chosen wrong weight. So what you need to do is that you need to go back and update the weights. How are you going to go back? You go back in the following manner. It's called back propagation. So this going back process is known as back propagation. And in the back propagation, what you do is you employ the gradient descent rule. Okay, what is the gradient descent rule? Let me remind you. A gradient descent rule is this: Wn plus 1 equal to Wn minus the learning rate times delta E by delta Wn. Assuming that this is just one weight. Okay, you have to do this for all the weights, right? Okay, and that way you update the weights. So once you have updated the weights, you are back to square one. You came back, your one shot is done. You came back to the input layer. Now you have to do it again. Okay, so you do it again using the forward pass, right? Using the activation function. You compare the cost again, you compute the cost. If it is good, you stop. If it is bad, you come back again and update the weights. And this goes on and on and on until you reach a reasonable cost estimate, a reasonable cost, right? I mean, ideally, as I said, it should be zero, but it is never zero, but as long as it's minimum. And you have to do this in an analytical method. That is why there is this, reason for a cost function, and you use calculus to compute the derivative and the gradient, right? And you see under what conditions this gradient is a minimum. Okay, so as far as the neural network is concerned, this is your capsule of the day, that there is an activation function. There is an activation, and there are several types of activation functions. And then there is backpropagation, where we employ the gradient descent. Okay, and then there are number of epochs. Okay, typically people fix epochs like 200 epochs, which means you have to do this 200 times, right? Or sometimes if your loss function is really robust and you have a very advanced method to determine, an update weight, then, it could actually, you could have the epochs as a dynamic measure. I really don't care. I don't really want to go to all the way up to 200 epochs. I might converge much faster. I might converge in 10 epochs or 20 epochs, right? Okay. So typical approach is you fix this. The typical approach is we fix this. So these are some vital components of an artificial neural network, okay, where it is activation function, gradient descent rule, and epochs. Okay, and also I should also mention, very, very important, is choice of your loss function. Choice of loss. Okay, choice of loss function. That is also very, very important. And there are several kinds of loss functions. I have shown you one, which is the mean square error. There are other loss functions such as binary cross entropy, mean absolute error, check loss, quantile loss, right? So on and so forth. But the most popular ones, which you will find in the literature a lot, are mean square error and binary cross entropy and cross entropy. Binary cross entropy is used for binary classification problems. Cross entropy is used for multi-class classification problems. Okay. However, each of these three loss functions have their own problems, but this is beyond the scope of this particular lecture to talk about the limitations, right? Okay. So this is roughly what it is. However, so you have some input data, right? So you know how to represent your input data, right? You know how to represent your cost. You also have some idea about, the gradient descent update rule. Okay. Now let me tell you what I should tell you is the following: is that how these activation functions actually play a role. Okay. All right. So when we talk about error gradient, like when you compute the error gradient, because your activation functions are involved in the forward pass, there has to be an error incurred because of that activation function as well, right? Okay. So your activation function has a stake in your error gradient computation. Okay. So that will be the next slide, and then I'll stop and take your questions. So tomorrow also, the first 15-20 minutes, I'm going to give a talk, right? And then Dr. Mathur will take over. So what she will do is that she will demonstrate this process of classification via her slides and a Python notebook that she will open up, and she will actually take the habitability data set, okay? And the activation functions that we wrote, we actually did not use this activation function in our work. We proposed a new activation function. She's going to talk a little, I'm going to talk a little bit about those activation functions tomorrow, right? And then she will take over so that you can connect, what I said today and what I'm going to say tomorrow, and what Dr. Mathur is also going to talk about tomorrow. Okay. All right. So I'll finish with this, error gradient computation, right? So that why we care about the activation function. Okay. So before that, I'll present a very neat, sort of schematics for the artificial neural network picture, right? So you have some weight combinations, and then there is this network, which I'm calling net, right? Okay. and then there is this activation sigmoid, and that gives with my output layer. Okay, so this is my input layer. Okay, so this is a very, sort of a compact representation of a neural network, right? So the idea is this: the output of the activation function has, how positive, the relevant weighted sum is. Okay, because based on that, you are actually going to classify to class 1 or class 2, right? So what I'm now tell you is an error gradient. We will talk about this error gradient again in relation to that particular sigmoid unit. So this is this sigmoid unit or this sigmoid activation, right? Okay, so this is the error gradient, right? Okay, now you know that this is, this is just a regularization term, right? And this 1/2 comes out, right? And then we have this, I'm going to skip this because I have already shown you these calculations, right? Okay. So this will be just TD minus OD, which is the difference between the target and the output, right? And then there would be a delta partial derivative with respect to the network, right? Because you see there is a relation between the network and the output layer, okay? And then delta network with delta WI. So there has to be a chain rule, right? This is nothing but the chain rule. Okay, now the delta OD with respect to the network, okay, is nothing but, now what is this output D? If you see the picture, the output D is nothing but your sigmoid activation acting on the network of D, right? So you can replace the output of D with this, correct? Now think about this, okay? So this is that delta sigma of X over delta of X, isn't it, right? Okay, so this can be construed in the following sense, that you can think of this as delta sigma over delta X, as if you are taking the partial derivative of the sigmoid activation function with respect to X. Now, I don't have the time to show this, but your sigma X is nothing but 1 over 1 plus e to the power minus X. If you do a delta sigma over delta X, carefully you will find that this is nothing but this, okay? So if delta sigma over delta X is this, then what is this guy going to be? This guy is nothing but OD times 1 minus OD, okay? All right, because your sigma is nothing but OD. And then you have delta net with respect to the weights, and this is nothing but your network is nothing but a weighted combination of weights and data, right? So WXI over WI, right? And this is nothing but this, okay? So therefore, if I combine all of this, what I get is the following. I get my error gradient with respect to one particular weight is the following, with a minus sign with a summation over all data points, the TD minus OD, which is nothing but my loss. Okay, this is my loss. Okay, times OD times 1 minus OD. Now, what is this? This is the slope of the loss function. This is the slope of the loss function due to the activation that you have employed, right? Times this xi comma d, which is nothing but the input data. In fact, this property is beautiful. I would like to show this tomorrow. Okay, right? But the reason why we care about the derivative of an activation function is because in the back propagation, when you are computing this error gradient, you actually are using this property. Okay, and this is the reason activation functions are required, and this is the reason we care about activation function. Okay, so just as a snapshot, okay, I started with some basic concepts of machine learning, how you can think of machine learning from a supervised learning perspective, where your data points have class levels. Then talked about regression and connected regression to hypothesis space. And then I also discussed how a regression problem can be thought of a classification problem, right? And what are the different types of classification problems, right? How you can convert a logistic or a linear regression problem to a binary classification problem, and what are the quantities at stake, which means the loss functions, right? How do we minimize the loss? How do we update the weights? Okay. And then finally, we spoke about neural networks or artificial neural networks, because tomorrow I would want to talk about how these methods are used on the data, okay, that we have taken into consideration, which is habitability classification of exoplanets. Okay. All right. So I think it's a good point to stop. Okay. And I will take your questions now. Rohit, yes.
Yes, sir. Am I audible?
Yes, yes, you are.
Yes, good morning. Okay, sir. For example, in gravitational wave data analysis, which is nothing but signal processing. So
Right.
we get data with a lot of noise in it. Now,
Correct.
when I apply machine learning to it, so what I do is I apply all the data points which is of signal, and I apply all the data, I give all the data points which of the known glitches that I know. And then machine is able to distinguish between a signal and a glitch. Now, in some instances, what happens is that the glitch mimics a signal. Okay, and when that happens, so the machine is going to learn in such a way, it is going to classify a noise which is nothing but a signal. So in that case, how does the machine, differentiate between a signal and a noise, a glitch?
Okay, first of all, I mean, if the number of glitchy signals, if the number of glitchy signals is significantly lesser than the number of clean signals, okay, all right, then you treat this problem as an anomaly detection problem, which means whenever you have a glitch, it's an anomaly. Okay, all right. So therefore, what you have to do is that you set the threshold very, very high. Either you set the threshold very low or you set the threshold very high. So if you go back to my first whiteboard where I was talking about this threshold, right? I mean, typically the rational way is to set the threshold as 0.5. Now, when you are saying 0.5, it's like you are on neither side, right? You are actually a centrist, right? But if you think of this, if you really want to detect some false positive, which I construe as a glitch, right? Then you depending on the goal of what you want to achieve, you have to set the threshold very, very high. So let's say instead of setting the threshold at 0.5, you are setting the threshold at 0.9. And you say that if it is beyond 0.9, then it's a glitch. Otherwise, it's a clean signal. So this is a very, very unbalanced classification problem. The particular classification problem that you are referring to is an imbalanced classification problem. If you approach it from the traditional machine learning or artificial neural network perspective, where we implicitly assume that the data points from different classes are balanced, you will not be able to solve this kind of a problem. Okay, all right. And so you see my point, right? You can also think of a statistical perspective, purely statistical perspective, that if you think that your number of glitchy signals are less, you can think of those as outliers. And then instead of treating that as a learning problem, you can actually employ some outlier detection method to figure out whether a signal is glitchy or not.
Okay.
Okay.
So we can also use Bayesian
You can use no. Yes, you can, but the moment you are using Bayesian, Rohit, you are back to the classification paradigm, right? I mean, you can do that, but then I mean, you have to figure out. You have to have your Bayesian posteriori function written in such a manner that it does not account for a lot of signals. As I said that I mean, most of these classical machine learning algorithms are tuned to the fact that your data is balanced. Okay, so if you have an equal number of glitchy signals as well as clean signals, go ahead, no problem. But I don't think that's the case, right?
Because we do come across such signals which really mimic the glitch, and then there is a problem like how do you feed the data into the machine such that the machine trains itself in order to distinguish between the signal.
So there must be some feature. Like for example, you can use a Dirac delta type discriminator to distinguish the glitchy signals from the clean ones. Like because a Dirac delta, right? A Dirac delta is just a one-off function. So
Yes.
you can use such approaches also. Also, you can use some filtering approaches a priori to weed out the glitchy ones from the clean ones, and then you can do the classification on the clean ones. It all depends on the number of glitchy signals that you have in your data. As I said, I mean, if I have to solve this problem, Rohit, I will, if I see that the number of glitchy signals are less, I will not use the standard machine learning algorithms. I will actually take the route of an anomaly detection problem, which is actually I will remove the labels. I don't want to know which ones are glitchy and which ones are clean. I will do it from a completely unsupervised learning perspective.
So we need more glitches to feed into the network in order to do that. The more the number of glitches, the better the result.
Exactly.
Yeah. Okay, sir.
Exactly. Obviously. Always. Yeah.
Thank you, sir.
Any other questions?
Yeah, so Snehanshu, with the spirit of what we are doing, I would request students tomorrow to log in with their laptops so that they can parallelly do it with Archana.
Exactly. Yeah. That will be great.
Yeah, because they need to learn to do it.
Right. Sure.
Yeah. Okay.
All right, then, if there are no other questions, we will see you guys tomorrow at 10.
Yeah.
Yeah, we'll do that. And
yeah.
they can think over it and ask questions tomorrow before you start.
Yeah.
Of course. You're welcome. Okay. All right. Okay. Okay, Nazam. Okay, Priya. Yeah. I'll talk about 15 minutes and then Archana will take over. Okay. All right.
Yeah. Okay.
Okay.
Thanks a lot. Thank you.
Thank you.
Bye-bye.
Bye-bye.
Anything to say? So we'll meet tomorrow at 10.
Yeah.
Bye-bye.